Okay, so we've looked at pretty much the kind of basic skills that we need with matrices. Now I want to just kind of do the interesting part. I want to show actually why matrices are used in maths, sort of show some of the applications. And of course the most obvious one is, a matrix is just a table of numbers. So basically if you've got loads and loads of information and loads of numbers in front of you, then and if you want to do something with that information, do something with that numbers, then if you represent it in a matrix, then you can do it all in one go, and you can actually do it really, really quickly. I mean, there's a piece of software called Matlab, which is used quite a lot of degree, and it stands for Matrix Laboratory. And basically what you do is you've got all this information, you stick it into a matrix, and the computer is just able to, it's got all the algorithms already programmed and coded into it. So you stick all your information in as a matrix, and then the computer pretty much does it for you. Okay, so the hardest thing is literally just putting it as a matrix. Okay, so that's one of the first uses. Believe it or not, a real world application is with Google. Google basically determines, you type your search in, you type your keywords in, and it tries to basically find what you're after for you. And it's a multi-billion-pound industry, of course, at Google and search algorithms. And it does it pretty well. I mean, obviously, there's a lot of search algorithms, a lot of research that goes into it. It's very complicated. But essentially, what it does is it looks at pages. So, say like if you have 3 pages, and it tries to basically find how many pages are linked to that pages. So it looks at the links between pages. Okay, and the idea is that if it has lots and lots of links, then it's going to be a really popular page. And it's what you're after. You're after that page there, and that's something called the page rank. The page rank algorithm, and what it literally does is it looks at the number of links, both into and also out of the page, and it represents that as a matrix. So it says, right, okay, the page in the top left-hand corner of the matrix. Let's say we have a matrix. The page, it basically, each element in the matrix is a page, okay? And it basically, this page here, for example, might have, 5 links to it. This page here might have 3 links to it. This page here might have, 1 link to it. Let's take a real-world example. Let's try and put some examples to it. Take Wikipedia, for example. Now, Wikipedia has got lots and lots of links to it. Because you go anywhere on the internet and anywhere which you're trying to find information about something, Wikipedia will have, its sources, pages will use Wikipedia as its source. And so therefore it will be linked to Wikipedia automatically. So Wikipedia will have lots of links to it. It also has lots of links from it as well. Because if you look at the bottom of Wikipedia, it has these citations, its sources. And it might be from, say, another website. So Wikipedia has lots and lots of links, which is why it often appears top or close to the top in what you're searching for. Okay, so literally what you do, I mean, if you think there's going to be hundreds of thousands, if not millions, of pages on the internet, and Google literally searches through all of them. I mean, it's got other algorithms going on underneath them to kind of determine which ones it should search and priority and stuff. But yeah, essentially what it's doing is it's looking at these pages, looking at the number of links it's got, and thinking, okay, well that's got quite a lot of links, so therefore I should put that relatively close to the top. And 9 times out of 10, it is what you're after. When you combine that with other algorithms and such like as well. But yeah, I mean, hundreds of thousands of pages. If you tried to perform an algorithm on each one of those pages, it would take, even if each one took 1 second, say, and you had 100,000 searches, that would take 100,000 seconds just to pull up a search. Well, Google's able to do it in sort of milliseconds. Yeah, why? Because it's able to put it into a matrix and perform that one algorithm on that whole matrix all at once. Okay, so it's very, very quick, is what I'm trying to say. Okay. Now, one of the applications of matrices that you look at in your course is to do with transformations. Okay, taking a shape, transformations. You take a shape and you want to move that shape. So this shape will have a coordinate, say. Let's just take a square. And it'll have coordinates. Usually you'd look at the corners, but it might be a really complex shape, so you just take however many coordinates you want. Okay, and then it moves it to another shape, and it moves it according to the coordinates. So this coordinate will move to here, this coordinate will move to here, this coordinate. So basically what you're doing is you're rotating this shape, in this example. And how does it do it? So it looks at the coordinates and it basically says, right, okay, where does the new coordinates end up? Okay, so that's quite a neat sort of idea to do. And the way that it does it is basically then you build a coordinate system around this shape. You put this on say like a Cartesian plane, and then you can map these coordinates, and then you can produce this matrix of coordinates, and then, in the exam, for simplicity, you take the simple shape, and because then you've got less coordinates. But in reality, you would use this with really complex shapes and really complex graphs, for example. And so basically anything which has coordinates, and then you sort of apply this transformation on it. So it basically does all these points at once. If you've got hundreds of thousands of points, it can do it all at once. If it's a really complex graph, you can transform all of these points all at once rather than doing them individually, which takes sort of quite a lot of time. Now, how do you produce a transformation matrix? Well, the way to go about it is to just take the simplest coordinates you can think of. And the simplest coordinates will be 1 across and 0 up, and 0 across and 1 up. So you're basically taking a coordinate in each plane. Okay, so a movement in each plane. You're moving in the x plane, you're moving in the y plane. When you represent this as a set of coordinates, so this point here is 1, 0, and this point here is 0, 1. Okay, so 1, 0 and 0, 1. You produce your coordinate matrix. Well, that's the identity matrix. That's why I say it's the simplest possible coordinate matrix that you could get. Keep it simple. If in the exam it's asking, right, okay, find a coordinate matrix or a transformation matrix which rotates through 90 degrees around the origin. Okay, so you draw something like this out. You draw the simplest one you can think of. You can take any matrix you like. You can take all sorts of coordinates you like, but take for simplicity this most simplest one. Take the identity matrix and take it in 2 planes. It'll only ask it in 2 dimensions as well. And what did I say? Right, we'll rotate it 90 degrees anti-clockwise about the origin. Okay, so 90 degrees around about the origin. So this one here will go through 90 degrees anti-clockwise. So it's going to end up here. So in other words, 1, 0 is going to go to 0, 1. Okay, and then 0, 1 is going to go down here. It's going to go to negative 1, 0. So 0, 1 is going to go to negative 1, 0. Okay, so this is, we want to basically find out what is this transformation matrix. Well, that is it. Okay, that is a transformation matrix. That's what, it's as simple as that. You can just simply read it off. You just look at the identity matrix, you perform your transformation, and you end up with your transformations of shapes. So that's really useful. And remember, when we're doing transformation matrix, we produce our coordinate matrix. We produce our coordinate matrix. Let's say we have a coordinate matrix A. Okay, then we've got a transformation matrix, let's say Y. Okay, so then we do Y, and then we end up with another. We end up with our coordinates, our new matrix over here, after we've performed transformation to it. So let's say we want to perform A, then we want to perform the transformation Y. But then let's say we want to do the transformation X. Then we stick it out the front. We always stick it out the front, and we always work outwards. So this is our coordinate matrix here. This is our coordinate matrix here. This thing at the furthest point on the right, that's always our coordinate matrix. And then the order which we do, let's say this is Z, this could then be N, this could be P, all of these are transformation matrices. Basically, the order which we apply the transformation matrix, we always work outwards, we always work left. Okay, so it's Y first, then X, then Z, then N, then P, and so on and so on and so on. So basically, as we move away from our coordinate matrix is always the furthest point on the right, the order which we apply our transformation matrix, we basically work left. Okay. Hopefully that makes a little bit more sense. I have done other examples of transformation matrices in sort of other videos when I've been going through exam questions, so it might be worth watching those. But this is just basically going through the basics, building up a little bit of intuition, and showing where matrix algebra is actually useful.